For more than a century, physicists have tried to find a unified theory, a single mathematical framework capable of describing all of nature's forces. Albert Einstein, who unified space and time in his special and general theories of relativity, pursued this goal for over 30 years, never succeeding. Today, scientists are continuing the quest, seeking to combine general relativity, describing the universe on large scales, stars and galaxies, with quantum mechanics, describing the universe on subatomic scales. Each of these two theories works amazingly well in its own domain, but put them together, like in the dense center of a black hole, and the math falls apart. In the 1970s, scientists came upon a potential solution, but from an unexpected starting point: studies of nuclear processes.
In that era, we were trying to understand the strong nuclear force, which is the force that holds the nucleus of the atom together. And that was a complete mystery how to do it.
In trying to solve that mystery, physicists were led to a promising equation that seemed to describe vibrating strings that would hold together atomic constituents. But within just a few years, a different theory proved to be the right solution for understanding the strong nuclear force, and so strings no longer seemed necessary.
Almost all of these several hundred people stopped working on string theory at that time, and only a handful of diehards continued to pursue them. The few of us who continued working on string theory felt that the mathematics was so beautiful and compelling that this theory had to be good for something.
Much like Einstein, who spent long periods working on ideas outside the mainstream, Schwartz and his colleague Joel Scherk continued to explore string theory.
We realized what string theory was good for, and that was as a quantum theory of gravity. And at that point, I was convinced that this was what I would be working on for the rest of my career.
Schwartz was proposing that string theory, which had failed as a theory of the strong nuclear force, was actually the solution to one of the biggest problems in all of physics: uniting gravity and quantum mechanics. When Schwartz excitedly announced this prospect, few people paid any attention. The field just wasn't ready. So Schwartz and a new convert, Michael Green, spent years developing the theory mostly on their own. Then, in 1984, they achieved a breakthrough, showing that the mathematics of string theory deftly avoided potentially lethal technical issues. And this time, the community of physicists heard them.
Princeton, between the university and the Institute for Advanced Study, you had almost half the experts in the world who were working on related topics. And I am told that at that point, almost all of them dropped what they were doing and became string theorists.
As string theory rapidly progressed, there was a sense that research was but a few years away from uncovering the final and unified theory of physics. More than 30 years later, the goal of a fully unified and thoroughly tested theory has yet to be achieved, but enthusiasm remains high. String theory has come closer than any other attempt to go beyond known physics and tackle the grand challenge of unification. But the question remains: is string theory an elegant mathematical chimera, or are string theorists rapidly approaching the realization of Einstein's dream?
Thank you. So, welcome to tonight's program, which is focusing upon a really ancient project, the project, as we described in that little segment, project of unification. And you can really trace the human urge to try to unify our understanding going all the way back. I mean, Democritus, long time ago, imagined that reality amounted to atoms and the void. That's all that there was. Galileo spoke about the book of nature being written by God in the language of mathematics. That would be the unifying framework, describing things all in terms of the symbols that we use to articulate mathematical equations. And as in that little piece, and as well as many of you no doubt know, Albert Einstein spent 30 years trying to unify our understanding of the laws of physics, but ultimately came up empty-handed. And what we're going to discuss here tonight is the next chapter of that story, a story that is ongoing And we're going to break down the discussion into 3 conversations, which very roughly speaking will cover the past, the present, and the future of unification. There will be overlaps, so that way of thinking about things is not completely accurate, but that's the general progression of the evening. So let's get right down to it. And we have a number of guests who are leaders in the field and thinking about these kinds of ideas. And the first guest this evening is a professor of natural philosophy, physics, and astronomy at Dartmouth College. He's a fellow of the American Physical Society and winner of the 2019 Templeton Prize. Please welcome Marcelo Gleiser. So, Marcelo, thank you for being here today.
My pleasure.
And, you know, when we talk about unification, we know that throughout history there have been many steps en route to the approach that some of us have been pursuing. In fact, you pursued at one point as well, string theory. And we have a little roadmap that we can bring up on the screen, which kind of shows some of the key steps. Now, obviously, there's a lot on this, and we're not going to be able to cover it all. But what I'd like to do in our conversation is sort of start at the bottom left-hand side, which many people view as the first step in the modern program of unification, which is putting electricity and magnetism together. So can you take us a little bit through that history, maybe going back to Faraday and Maxwell and what happened?
Sure. So we're talking about early 1800s, and people had some experience of electricity by having shocks whenever they, had a very dry environment, and they would touch like a doorknob or something. And they knew about magnetism since, for a long time. But at least in 1601, the court physician of Elizabeth I, called William Gilbert, he wrote a book about magnetism, and he realized that the Earth was a giant magnet, and that's how compasses work. They're basically aligning with the north magnetic pole. And so these two things were considered to be very different, and until Michael Faraday started to make some experiments, and actually even before him, Hans Christian Ørsted in Copenhagen, he realized that if you had an electric current going through a wire, a magnet would move. And so there was this, and it was sort of an accidental discovery. He had a bunch of stuff on the table, doing demonstrations, and then he figured it out. So clearly there was a connection between the two, and it took Michael Faraday's brilliance, to develop this, and he realized that it wasn't just an electric current that could affect magnetic compasses, but it was actually magnetism, just like the picture is showing up there. That he realized that if you move a magnet, you can create an electric current as well. So there was clearly a connection between the two. And he started to visualize this, and this was also very useful for us with the notion of a field, that basically the presence of these sources of magnetism or electricity, they spread around space, and this spreading around space is how, say, a charge will feel the presence of another charge through this field, right? And then later on came Maxwell, maybe a couple of decades later, and he then elaborated these connections between electricity and magnetism, showing that you actually have a set of 4 equations, right? The ones that you see on a t-shirt, right? You have, and God said 4 equations and there was light, because what Maxwell did was he wrote the equations of how changes in electricity and magnetism, because of different sources or even in empty space, propagated, and he realized that the propagation was at the speed of light. So clearly, the way light should be interpreted is actually as a moving electromagnetic field in space, and hence the unification of the two.
Now, those 4 equations that are on T-shirts, it perhaps is worth noting, his formulation was a little more complicated.
Yes.
So, as we mature in our understanding in the field of science, and this will be a theme actually throughout tonight, we get better and better at finding ways of streamlining, combining, unifying, in a sense, even in the mathematical notation. So today we have these 4 equations, but back then it was kind of a mess.
And in fact, if you really use special relativity, which we'll talk about soon, you can actually write all of them in one equation.
Yes.
Which is beautiful, right?
Exactly. So why don't we turn to that? So this is our first unification, electricity and magnetism, this deep, unexpected connection, Maxwell codifies it mathematically in the electromagnetic equations that we all teach to undergraduates in physics around the world. Einstein perhaps is rightly credited with the next step in the road toward unity by recognizing an unexpected link between space and time. So can you sort of take us, you already mentioned light, so the speed of light being constant is a vital part of that story as well. So why don't you take us through that?
So Einstein realized that there were some inconsistencies with the formulation of Maxwell's equations, and nobody could figure out exactly what was going on. One of the big mysteries in the 19th century was that, as we know from intuition, every wave propagates in a medium, right? So if you throw a rock on water, the energy of the rock is going to hit the water. You're going to see the waves propagating on water. Here I am talking to you. That means you have sound waves growing through the air. If there is no air, there is no sound, no explosions in outer space. So every wave seems to need a medium to propagate. So the question then became, okay, so where does light propagate, right? And that was an important question because you can see stars, which means the medium should be transparent, right? And it can't have any viscosity because otherwise the planets would slow down and fall into the sun. So it had a transparent, no friction, no weight, clearly, and it had to be somewhat rigid, actually quite rigid, to propagate waves at that kind of speed. So it's kind of like a magical thing, which people call the ether, right? And for many, many years, Maxwell tried to create models of the ether to kind of make sense of all this. And in 1887, there was a very famous experiment, actually by American physicists Michelson and Morley, where they actually were going to show how the ether interferes with the propagation of electromagnetic waves, and they couldn't find it. So that was like a mystery for a while. How is that even possible, right? And only in 1905, Einstein came up with his new way of thinking. So he creates the special theory of relativity. He's 26 years old, and he comes up with two essential postulates. One of them, very reasonable, known way before, from the time of Galileo, that the laws of physics should be the same for everybody, at least everybody moving with constant speeds relative to one another. Makes sense. Otherwise, how could you actually have laws of nature if they change when people moved around? And the second one, which is a really amazing one, is that the speed of light should always be the same for any observer, irrespective of how the source is moving, right? And with these two things, he showed that you could actually, that the speed of light and the way we make measurements of distances in space and of moments in time or duration in time were affected, and that's where you have the very strange idea of time dilation, time moves slower if your clock is moving, and space contraction where a rod, for example, or if you're moving close to the speed of light, you kind of shrink in the direction of the motion.
So schematically, it's as if space and time, as we see here, are kind of adjusting themselves in order to keep this other thing, the speed of light, from changing, keeping it constant at whatever units you like. This one is miles per hour. Yeah. But this constancy of the speed of light winds up establishing an unexpected unity between space and time. They need to work together in order to keep the speed of light constant. So that's sort of the second big moment in the modern route to a unified understanding of nature. Now, after the special theory of relativity, you mentioned that's 1905, Einstein is 26 years old. He could have stopped there, right? I mean, that's the kind of achievement that many of us would say, there's not much left for me to do. But for Einstein, he was just getting started, right? Yeah. So the next step is he goes further and brings the force of gravity into the story. So just tell us a little bit about the next 10 years and this further unification of space-time and gravity.
So it did take about 10 years for Einstein to really get to the end of the story, but his first intuitions were not much later, after 1905. He said he had his happiest thought, right? Which was the idea that if somebody, it's kind of dramatic, but if somebody is falling from a rooftop, that person won't feel his or her own weight, right? So you're sort of, this idea of weightlessness, that you're falling through space and you feel weightless, that was his intuition. And you know all this because living in New York, you go up and down elevators all the time, and when you're going down an elevator from a high rise very fast, you feel lighter, right? Now, if the elevator just falls, you feel weightless. So Einstein realized that to talk about motion that had acceleration in it, you also had to talk about gravity. So as he tried to expand his theory of special relativity, the special here was about motions at constant speed to motions with acceleration, he realized that that new theory had to be a theory that included gravity as well. And that's a beautiful thing, because as he goes to formulate the theory, which we would say it's perhaps the most beautiful theory in physics, we're biased, of course, because that's what we do, right? That theory was a theory that related gravity not to this kind of mysterious action at a distance, which is what Newton did. He, in a sense, did a unification of the laws of gravity on Earth and in space as well. But it was a theory that described gravity as the curvature of space, and also it affects time and how time flows if you have a very strong mass, to do that. So that was his next big step. So he realized that, and of course, we should also mention the connection between mass and energy that is a byproduct of all this. Yep. So in 1905, there was a second paper on special relativity, which is the famous E equals mc squared paper, right? In which there is a deep connection between mass and energy, and that mass had the property of affecting the geometry of space, and because of that, there is a change in the motion, say, of planets around the sun, which can be explained by this beautiful theory.
So we now have this part of the map fairly set. Now, in 1970s or so, there was another important moment that we don't really have time to go through, but it's quite analogous to what Maxwell did, putting electricity and magnetism together. And that's the electroweak theory, which puts together another force of nature, which is the weak nuclear force, together with the electromagnetic force. They also proved to be different aspects of a single ingredient called the electroweak force. So we get to this point by, say, roughly 1980. Now, we could stop here, right? We have gravity in the story, we've got electricity, magnetism, weak nuclear force, and so forth. But we want to continue to move toward unity as best as we can. Now, the next steps, however, go beyond what we have experimentally tested. So the question is, what do we do? So we can give a sense of the equations behind this, which is not a bad thing to show, because it helps to motivate us to go further. So what are we looking at right here?
Look at that, from one equation to this. That's not good, right?
Yeah.
So this is essentially what summarizes what we call the standard model of particle physics, which basically is a description of all 12 particles that we have measured in the laboratory, especially like at the Large Hadron Collider at CERN, and before that at Fermilab, these huge machines that can actually find these particles of nature. So there are 12 of those. And then there's also the Higgs, which is the particle responsible for giving mass to all the other particles. And basically, this is the state of the art in a sense that we can actually measure and feel comfortable somewhat about what we know. And this describes essentially three fundamental forces. Gravity, forget it. Gravity is not even there, right? Yep. So this is not about gravity. This is about electromagnetism and the weak and strong nuclear forces. So the weak nuclear force, very quickly, is the one responsible for radioactive decay, for radioactivity, for having, how the sun powers itself in a sense. And the strong nuclear force is the one that keeps, say, the atomic nucleus together. You have a bunch of protons, they're all positive, they should be running away from one another, but they're glued together by the strong force, who also keeps the quarks, which are the fundamental particles you see here, inside of protons and neutrons, okay? So this is it. One thing about the electroweak unification, though, is that it is not as perfect as we would like it to be, because the way we think about these forces, that every force has what we call it a coupling constant, but basically a measurement of how strong that force is, in a sense. So gravity has the G for Newton's constant, right? Electromagnetism has E for the electric charge. And it turns out that the electroweak unification does not have a single coupling constant to connect the two. It's still describing the two forces somewhat differently. They seem to reveal similar behaviors at very high energies, which is the inspiration.
Part of the motivation
exactly,
to go further.
for moving on.
So we can actually show the rest of the roadmap. But the roadmap from here, unlike this equation, which is experimentally tested, as we go further, these steps are not experimentally confirmed. In fact, we can even go further and show the rest of the map. And basically, everything that's above row 3 is hypothetical. And we have been developing the mathematics behind these next steps in the road toward unity for 3 decades, if not longer. So the deep question that we face, and I posed to Marcelo, without having the experiments, without having the observations, without having the data that will allow us to go above the 3rd row, where we do have experiments and data that confirms everything, where does that leave us? And you have very specific views on whether we're perhaps doing the right thing and pushing forward with a purely mathematical motivation to go further.
Right. So a little bit of history is that in '84, I was doing my PhD at King's College, and when Schwartz talked about his, and Green, talked about their discoveries in the string theory, I'm like, wow, this is it. You got to work on this. It's beautiful. It's, at the time, the idea was that you'd really find a unification of the 4 known forces of nature, which is something we should talk about at some point. 4 known forces of nature is very important. Yeah. So I jumped into this and tried hard, like you did, and a bunch of other people in our generation, tried to make sense of all of this. And the program was very sound in the sense that behind our expectation of trying to find this unified formulation, there were very concrete predictions, right? I mean, so in order for these string theories to work, you had to impose a new symmetry of nature called supersymmetry. And supersymmetry had a very specific prediction, which is basically to every particle of the standard model, the 12 particles I talked about, there should be a mirror world, so to speak, of supersymmetric particles. So the electron has a supersymmetric cousin called the selectron, the photon, the particle of light, a photino, and so on. And hopefully, with big machines, you should be able to find them, right? That was the big expectation of the time. So you build bigger and bigger machines, and one of the goals of the Large Hadron Collider in Switzerland was not just to find the Higgs, which beautifully was done in 2012, but to also find the lightest of all supersymmetric particles. And it's not there. At least we haven't found it yet, right? And so that rules out some versions of supersymmetric theories. And then the question is, what do you do as a theoretical physicist at this point, right? That you basically spent decades of your life working, and of course we're going to have another guest here that is a real expert on this. You spend decades of your life working on this thing, and you're placing your bets on this, and it's not coming true. So what are you supposed to do at this point, right? So do you say, I'm sorry, I was wrong, and you move on to other things? Well, it turns out that supersymmetric theories, they're so flexible in their formulation that you can always kind of change the parameters in ways where the particles that you were supposed to find are so massive that you could not find in the Hadron Collider, which basically means is a theory that in principle cannot be killed, right? Because it could, you say, look, I haven't found it, no problem. When we have an accelerator which is 100 times bigger, we'll find it. And then you can always, to a certain extent, drill this up and create more and more complicated models, right? And I don't think there is anything wrong with that, because there is what I would call a creative perplexity right now related to this, because clearly we want this beautiful Platonic dream of simplification of nature to be true, but at the end of the day, nature is the ultimate guide, and we have to listen to nature, because that's the whole goal of physics, is to explain what the world is like, not what the world is like we would like it to be. And so this is a very interesting time for us right now, because things that we thought were going to be definitely discovered are not quite being discovered. And the moment now is a little complicated, and it's a very important moment because what we decide to do now is going to impact the field of particle physics for decades to come, because these accelerators are very complicated machines and it takes decades of planning and a lot of money to make them work.
Now, you have a particular philosophical orientation in terms of human knowledge more generally. And I think you even have a slide that you gave us that summarizes that perspective. So just take us through your view on the program to sort of try to find the deep fundamental laws that will describe all physical phenomenon versus your view of how knowledge progresses.
Right. So this is actually the title of a book of mine called The Island of Knowledge. And it's basically a metaphor for how we humans understand the world around us. So the idea is very simple. If everything that we know about the world fits in an island, right? As we know more about the world and about ourselves and about our place in the universe, this island grows. And as every good island, it's surrounded by an ocean, and I call mine the ocean of the unknown. So science, in a sense, is an exploration of what we don't know, right? That's the whole point. We are expanding our views, we're expanding our tools of exploration. I call them reality amplifiers, our telescopes, our particle detectors, in ways that we can see more than we could see in the past. So that is how we advance, right? So as the island grows into this ocean of the unknown, the paradox of knowledge, though, is the fact that the boundary between what is known and what is not known grows. So that means that as you learn more about the nature of reality, you become equipped to ask questions that you couldn't have asked before because you had no idea. Simple example of that, the telescope. So before Galileo built a telescope, in it wasn't his first, it wasn't the first telescope, but he said it was. He was smart. And then he sold it to all the, the nobility of Venice, made money, etc. But so he builds this telescope and he looks at the sky and he sees things that no one had ever seen before, right? And that was a profound change in our worldview, and with many implications, religious implications, social implications, philosophical implications, because of this expansion of knowledge. And because of this new machine, he was able to ask questions about the world, about the universe, that no one could have asked before, right? And so to me, this is very much how science advances. It's through this expansion into the unknown that allow us to begin to ask new questions. For example, we couldn't have asked anything about supersymmetry before we had the idea of supersymmetry, and now we're looking for it and we don't find it. Let's assume we could find it. And then this whole new way of thinking about the world is going to happen because of this new theory.
Now, having said that, presumably you do agree that there are chapters in, say, the Book of Knowledge that can be fully written. They open up other areas, but it's conceivable that we will have the theory that describes all of the fundamental forces, describing all of the fundamental particles of matter, how they combine and the kinds of behaviors that aggregates can play out, maybe something that is beyond our ability to ever fully articulate. Like, I don't think a fundamental theory will ever, for instance, be able to predict the kinds of socks, the color of socks that I have on tonight. I don't even know what I've got, but I've got purple and black right now, right? So it's unlikely that we'll be able to undertake those kinds of calculations. Yeah. But what about the fundamental theory that's on our map toward unity? Is that something that you think fits into the unknowable, or is that something that you imagine could be knowable?
Right. So that's a great question. So I think in terms of what philosophers like to call the map and the territory, okay? And the idea is that we are map makers. That's what we do. Our theories are maps of what we see of the world, right? The territory, if you were to, there's a famous short story by Jorge Luis Borges about the map makers that wanted to make a very perfect map. And every time they improved the map became bigger and bigger and bigger until they had the map as big as the country. And that was the best map they could ever have. And clearly it was a useless map, right? Because maps are descriptions of what we can see. And so the point is that our theories are maps of reality guided by what we can eventually measure, right? And given that our machines, our technologies can never give us a complete picture of reality, there is always a higher energy scale until you get to the Planck scale, and we are very far from that. That is really very dangerous, I think, to assume that the four forces of nature that we know now are the only forces of nature that exist. So what I would like to point is that the best that we can do is to construct a unified theory of the known forces of nature. But to make a statement that that is the ultimate theory of how the is, to me, really unjustified by the way we do science.
Right. But typically, of course, I think most physicists have the attitude that all theories are provisional. They're the best description that we have at a given moment of the physics that we have access to.
Right.
But, you know, we all know that even Einstein's equations will be modified as we try to understand the universe in more extreme realms than his equations were developed to explain. So let me finish up with one question, because we only have a couple minutes before I need to move on to the next participant tonight. It's kind of a big one, but maybe you have a quick thought on it. If it's too big, just tell me, hey, I don't want to talk about that, and we can just end it right there. But when we talk about complete theories, I'm often asked, what do you think about Gödel's incompleteness theorem, and what does that imply for this program? Gödel, of course, famously wrote down a theorem a long time ago that basically said that if you have a system with axioms that are sufficiently rich to be able to describe things like arithmetic, that either the system will be inconsistent, or if it's not inconsistent, there will be true statements within that system that you'll never be able to establish to be true within the system itself.
Right.
Does that have any bearing, in your mind, on the program of searching for the deep fundamental laws of physics?
I think it does, in a sense, because it's kind of like the Russian dolls, right? I mean, so to bypass the Gödel's incompleteness theorems, you have to create a bigger system that encompasses that one, right? But then, of course, that bigger system is going to have the same problem, and then a bigger system, and then a bigger system. And the problem is that the idea of completeness of knowledge is a very dangerous one. And I think Gödel proved that in mathematics. And the notion that in physics, because we do need to validate empirically what we're doing, it becomes even more complicated because we depend on technology, on machine. And so I'm very happy with the notion that we can't know everything there is to know at the level of fundamental particles, because that's what's going to keep us working harder to move on and on. And to me, is the process, this quest for knowledge that really matters, not so much the end product.
And it gives us something to do going forward. Ultimately.
Exactly.
Yeah,
absolutely.
All right, it was great talking to you, Marcelo. Thank you so much.
You're welcome.
Appreciate
Thanks.
that.
No problem. There's my water. Thank you.
Okay, in the second part of the conversation, we're going to turn specifically to string theory proper and try to get a sense of how far we've gone in connecting it to the physics of the real world. Imagine I have a beautiful tree that's filled with oranges. And I ask myself, what is the orange made of? How do I answer that question? Well, I want to look deeply inside the orange, so I magnify it. And I magnify it again, and if I keep on doing it, deep inside, sooner or later, I begin to see molecules come into view. But molecules are not the end of the story, because the molecules, I can enlarge them. And if I make them big enough deep inside, I begin to see atoms. Atoms are not the end of the story, too, because we have electrons zooming around the nucleus. Deep inside, mostly empty space in the atom, but deep inside, we see the nucleus. So if I grab that and magnify it, I see that the nucleus is itself made of particles, neutrons and protons. And if I grab one of the neutrons and magnify it, I find yet further particles, little tiny quarks inside. Now that is where the conventional ideas stop. String theory comes along and suggests that inside these particles there is something else. So if I take a little quark and I magnify it, Conventional idea says there's nothing inside, but string theory says I'll find a little tiny filament, a little filament of energy, a little string-like filament. And just like the string on a violin, I pluck it and it vibrates, creates a little musical note that I can hear. The little strings in string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves. So a quark is nothing but a string vibrating in one pattern. An electron is nothing but a string vibrating in a different pattern. A neutrino, nothing but a string vibrating in a different pattern still. So if I take all of this back together, I have my ordinary orange, and if these ideas are right, they are speculative, but if they are right, deep inside the orange or any other piece of matter is nothing but a dancing, vibrating cosmic symphony of strings. That's the basic idea of string theory. What we want to do now is to see how far we've gone toward establishing or refuting that this idea actually describes the world around us. And for that discussion, I'm pleased to bring out our next guest. He was recently elected to the National Academy of Sciences and is currently writing a book on the big questions confronting particle physicists and cosmologists. Please welcome Michael Dine. Good. So Michael, thanks so much for joining us. And you know, we had this map of unification that we can bring back up, where we see at the top this proposed idea of superstring theory, also called M theory. Maybe we'll get to that in the course of our conversation. But the key question is that step of the story something that we can justify through experiment and observation? I mean, the mathematics is beautiful. John Schwartz spoke about it in the opening, that it puts gravity and quantum mechanics together. The left-hand side we understand well quantum mechanically. The right-hand side is problematic quantum mechanics. String theory puts that all together. So it's a beautiful, compelling structure. And the question is aligning it with experiment. Now, in the previous conversation with Marcelo, we spoke about supersymmetry, which is the super in superstring. And that, for a long time, was held out as the smoking gun, that we were going to prove the supersymmetric quality of the universe. So first of all, when we talk about supersymmetry, what does it mean for the spectrum of particles, the stuff that should be out there?
Okay. Well, I should perhaps back up a little bit.
Please.
And you wrote these equations, or you presented these equations for the standard model, and they look really ugly.
Yeah.
Okay, they're not really ugly. They're really rather beautiful. So the theory is spectacularly successful. Until recently, we were missing one piece, which was this Higgs particle. And there was a lot of speculation about what that might be, and now that's been found, and it acts sort of just like it's supposed to.
Right.
So we have this kind of very pretty story, and the thing that sort of excited a lot of the interest in string theory, and certainly part of your career, and certainly mine, was Andy Strominger, who we'll hear from next, is that string theory seems to be able to produce this standard model, at least in rough outline.
Right.
In a very remarkable way. So that's partly why I didn't want to bias this that way. This beautiful theory comes out.
Right.
Now,
when you say comes out very clearly, you mean like the vibrations of the string seem to give rise to the kinds of particles that we see on the left on this thing.
They bring in a very remarkable way.
Yeah.
And so that part is really quite pretty. Now, there had been, before string theory came along, there were reasons to think that might be there, mostly connected with puzzles related to the Higgs particle. And a lot of us thought, who worked on this at the time, thought maybe this idea was a little contrived. And then along came string theory, and among the things string theory did was, oh, there it was. Okay.
I mean, these particles naturally
these extra
emerge.
things,
Yeah.
these additional vibrations were there. And I certainly was, I actually should say, I was sort of dragged, kicking and screaming into the subject of string theory.
Is that true? Because I've read all your papers. I thought you were a gung-ho enthusiast.
No, I was, initially, I was part of this generation that viewed string theory as kind of passé, this thing as you saw in John Schwartz's argument. And there was a period where I would talk particularly to Ed Witten And I would say, how are you going to solve this problem? And he would say, he scratch his head and he'd say, I don't know. And then he would come back 2 days later and say, by the way.
By the way, I have a solution.
Yes.
You mean, yeah, right.
Yes. So I got quite nervous, and in particular, this fact that a lot of these features of supersymmetry were there, that we had speculated on, got me quite excited.
Right.
And I thought, I think in the spirit of things you said, that we're weeks away, and I better get to work.
Right.
But string theory, but I should say that it's sort of understood. In fact, supersymmetry is a little too much of a crutch in string theory. The only string theories we really understand well have exact supersymmetry. So all these other particles would be there. There were, in addition to the electron, which is so familiar to us, there would be this thing just like that, except just a little bit different, this electron, and it's not there. It's not there.
So back in the 80s when I started to work on string theory, all the somewhat more established scientists, such as yourselves, gave the impression that this was the next frontier of particle physics. We're building this big machine in Geneva, and it's going to find these particles. And that, I mean, tell us where we stand on that program.
So the truth is there were reasons to be skeptical about this program for a while.
Now you tell me.
For a while. I actually, if you listen to me carefully, as opposed to many of my friends, some of whom you are having in other parts of this thing, you would have heard me say that. But we're now in a situation that we have the Large Hadron Collider at CERN, which has now been running well for almost a decade, has both established this Higgs party, really established the Standard Model with exquisite precision, has allowed us to do all kinds of things, both experimentally and theoretically, which I wouldn't imagine we could do some number of years ago. Okay, but one of the things it has done is said, I think as Marcelo said, that if supersymmetry is there, the particles are heavier than we guessed. And Marcelo described the theory as rather elastic in a way. It's elastic, but it gets uglier as the masses of these particles get
beyond
larger.
the reach of the Large Hadron Collider,
Right. So to be specific, for example, what we know about the Higgs suggests that the supersymmetric particles, if they're there, are out of reach of the LHC and out of reach of a lot of the things that we currently contemplate. So it's an idea in some tension, in some trouble.
Yeah, I mean, I should say, I don't know, I recently did a sort of a quick survey. I was just curious on the fraction of the papers that I've written in my career that assume that supersymmetry is correct.
Right.
And it's a significant fraction. It could be as much as 90% of the work that I've done. So there's a certain kind of discomfort associated with the lack of finding these parts. Do you share that discomfort, or?
I don't know if it's 90% of my papers. It's a number, and yes, I share this discomfort. I think will come shortly to some of the, or a little bit, to some of the reasons why perhaps some of our ideas about where supersymmetry should be had a certain amount of hubris.
Yep.
So
let's change gears slightly then and talk about another key quality of string theory that is really quite iconoclastic, that it requires that the universe have more than 3 dimensions of space. This is sort of one of the other strange features. And we can just sort of, in a cityscape like here, you can consider the dimensions to be up, down, back, forth, left, right. And if you zoom in, according to the ideas of string theory, you go small enough, you're going to find extra dimensions of space. Usually we imagine that they're curled up really small in order that they evade direct detection as we look around the world around us. And strings are imagined to be so small that they vibrate within these tiny curled up dimensions of space. So depending on the formulation of the theory, there could be 6 or 7 of these extra dimensions. We understand that distinction quite well. The question is, Is it a matter of simply hiding away these extra dimensions that are sort of a weird mathematical feature of the theory, or is there a way that we might indirectly find evidence that these extra dimensions are actually out there? Could they be the smoking gun?
There are various ways to think about this question. I mean, I often, when I talk to students or lecture about this, say the real problem is that first you get kind of dizzy when somebody introduces you to this idea. And the next problem is they say how hard it is to, if they're curled up, to actually see any evidence.
Yeah.
So, and there have been speculations on the possibility that actually some of these extra dimensions would be large,
Yep.
sort of millimeters even size. So as you could imagine, sort of probing them with tweezers.
Right.
And people subsequently have done experiments and ruled out these kind of what people call very large extra dimensions. There is still a chance, my own betting is against it, that we could find evidence.
That we will not find evidence.
So I would bet against, but there is but I want to say there is the possibility.
Right.
And certainly people consider it, and people in doing experiments consider what might be the evidence and trying to exclude or place limits on these possibilities. But as you say, it also seems, I strongly suspect that while we may not know the whole picture, that extra dimensions will play some role in some larger understanding of the laws of nature.
Now, one of the things that excited me about this subject, we sort of talk a little historically back when these ideas were first really being developed back in the 1980s, the precise shape of the extra dimensions sort of played the role of a kind of DNA of the string theory universe, because the shape of the extra dimensions would affect how the strings vibrate,
Right.
and as you saw in the little opening video, how the strings vibrate determines the properties of the corresponding particle. So the thought back in the 80s was, if you understood the precise shape of the extra dimensions, you might actually be able to calculate those numbers in that crazy formula that we showed before that had within it, you probably couldn't see it. The mass of the electron, the mass of the quarks, the mass of the neutrinos, right. The mass of the Higgs, that all of that might be embodied by the geometry of these extra dimensions, a unity, if you will, of all those numbers inside the geometry, the shape of these extra dimensions. That program presumably was something that was appealing to you in that era as well. One of the problems, of course, is there's not just one shape. We're showing one shape over here.
Right.
I mean, tell us what happened in the 80s and 90s for the...
Well, you're actually more of an expert on this than I am. But they're really, and Andy as well, there has been a proliferation of so I should perhaps back up and say, basically, we don't really understand we understand string theory sort of. We don't really understand it that well. We can't write the equations as nicely as Maxwell wrote his equations. But we sort of know when we found a solution of the equations.
Right.
And we thought we had just a few at first. And some of them looked like, you yourself worked on examples which looked like they had lots of features of the standard model. But there has been a proliferation, so then now I don't know what the right way to characterize it, but many orders of magnitude of known solutions. And
so many different shapes, many different possible candidate shapes.
Many different features. So we're not, I personally am not an optimist that one could find the one.
Right.
I view this as a problem that one will have to more probe, at least for the moment, in a sort of statistical fashion, asking what's characteristic, what's generic.
As opposed to trying to find the specific standard model, if you will, find those generic features shared by all these shapes as far as the physics goes.
My fantasy, for example, is explaining, of these, if we're coming back to supersymmetry, a kind of question might be, among these, is it typical that the scale of supersymmetry breaking, the splittings between these particles in their masses, is that something you should see at the LHC? Is it something that is somewhat larger scale? Could you figure that out?
Right.
And there's so many, could you sort of do some statistics of these and figure that out?
Now one other sort of astounding development in the late 1990s was the discovery that the expansion of the universe is actually speeding up. It's accelerating. And that was an unexpected, I think, development, certainly for me, presumably for you as well. We thought that the expansion would be slowing down over time. Gravity tends to pull things back together, but yet it's going faster and faster. To explain that, we needed to introduce this idea of dark energy that yields this repulsive push. The weird thing is the amount of dark energy is a bizarre number, right? It's starts with a decimal point, has a huge number of zeros after it, and this is sort of giving you a feel for it right here. So this number, trying to make sense of this observed number, indirectly, some people have other approaches. What has this done to the program of trying to connect string theory to the observable world?
So let me go back to supersymmetry first and to kind of explain what the tension was I described before and why I claim I was at least cautious.
Okay.
And so you've drawn here something, I didn't count the zeros, but I'm guessing you have about 120 or so.
There are 120 zeros. You're right on target.
And so supersymmetry was proposed to explain a similar problem where about 32 zeros.
Yeah.
Okay. So 120 is a lot more than 32, and it is in many ways a more fundamental problem. And we don't have really good ideas. We have an idea, which we'll talk about, to perhaps understand this. None of us are totally in love with it. And it's different than the idea of supersymmetry. So this is something we knew even before this was discovered that there was some tension here, significant tension here. And it's gotten just worse with this understanding and discovery.
And the other idea, presumably you're referring to, is the multiverse idea. Yeah.
Yes.
So why don't you sort of take us through the thinking?
So you've already sort of alluded to it here, that we have this proliferation of solutions of the string equations. Actually, I should perhaps back up and say that the multiverse was proposed before string theory. In a sense, it was a form of this was proposed by Steven Weinberg, who basically predicted the dark energy. So he basically said a way you might understand the dark energy is to imagine that there are actually, if you like, many universes with different values of this crazy number, most of which are big. I think you have a slide that shows this, most of which don't have so many zeros.
Yep.
But there's just so many that a few of them have these zeros. And if you're some kind of Star Trek-y kind of figure, here we are, I think, if you're exploring these many universes somehow, once in a while you'll find one with this very small number. And what's special about these ones with small numbers, he pointed out, is only those will have stars, planets, things where people or intelligent beings or less intelligent beings can be.
Yep.
Okay, and this idea gives pause, but it also successfully really predicted the amount of dark energy that's observed. So string theory looks like it might provide a setting for this idea, this multiverse. It has the potential, we're not sure. It's also actually related to our lack of understanding of how supersymmetry is broken in string theory. But there's the possibility that string theory works this way.
So the idea is that you could have all these different universes with different shapes for the extra dimensions, giving rise to different amounts of dark energy.
And different values of all those coupling constants, of all those numbers in the slide. And
now,
so
some people look at a solution like that quizzically, and they say, look, you guys have all these problems. You don't have a unique shape for the extra dimensions. You don't have a unique universe. And in order to leverage those problems, you imagine that maybe all these universes are out there and that we're just one in this grand collection. And aren't you guys just giving up, or even worse, papering over the problems that your theories have? I mean, how do you respond to these?
Well, I remember a talk that David Gross, noted string theorist, gave where he kept repeating Churchill's line, never, never.
Yes.
And there's a question of whether it's giving up. So my own personal attitude, and now I'm not speaking of a great movement or something, is that a way we might deal with this is to understand the statistics of these many states. So I think for those of us who now live in a world of big data and so on, you could imagine, you somehow sample all these and you have some idea what's typical.
You're right.
And there's one approach, one aspect of this, which is related to things that you have worked on as well, is related to the fact that most of these many universes aren't stable. They're sort of like unstable elements. They would decay after a
They
little
fall
while.
apart quickly. Yeah.
Fall apart and quickly. And we want to stick around for, at least 15 billion years or so. And these would fall apart typically in fractions of seconds. Okay? So you could ask what might account for what among, as you sample these, which are the stable ones? And it turns out, interestingly enough, the stable ones tend to be the supersymmetric ones. So this doesn't quite predict supersymmetry at the LHC, but this is in the class of things we might hope to address.
Right.
But I should say, there are many people who reject this whole way of thinking entirely.
So, we're getting toward the end of our time here, and I wanted to just ask you the following. I don't know if this is a personal question or all, but if we go back to your frame of mind in, say, the 1980s, when there was this incredible excitement about supersymmetry, string theory, supergravity, unification, if you were to project forward from the mid-1980s to 2019, how have we done?
Well, it's a good question. First, so I would say that we actually, a little bit our focus has changed.
Yeah.
And in some ways, I think, in fairness to myself again, there's something called the Dine-Seiberg problem, which basically deals with some of the problems we faced. And I think we've come further to addressing it than we actually have. I might have guessed. So, but we also have, I think this is something that Marcelo said, we've also sharpened our questions. Okay, so in ways that perhaps aren't even on these slides. We understand the dark energy has now given us a sharp set of questions. The dark matter, which I don't think has figured so much in our discussion,
Yep.
Has also. And again, in a qualitative way, string theory gives us some handles on these questions as well. So I'm keeping busy. I think there are lots of interesting questions. I think some things are hard. I mean, I think the fact that, I want just to pause and say that the fact that the Higgs particle is there and actually acts, it's not something I would have really expected. It's really a very remarkable.
Comes out of a piece of mathematics, a natural solution to a
Right.
problem,
Well,
there
absolutely.
it is. Yeah.
Absolutely.
So looking forward, final question. Imagine that in the next 20 years, we don't find supersymmetry either at the LHC. Maybe we have a new collider. It doesn't find any evidence for supersymmetry. We don't find the dark matter, so we don't have that as an input to our story. We sort of don't have any connection to observable experimental physics. What do you think happens to the program of unification, the program of supersymmetry in that situation?
I think it goes on, but I think now I am being personal here. I think, well, first of all, of course, in 20 years, I'm older than you. In 20 years, I will be, it won't matter. But I think it will go on. But I think it will be a narrower field, and it will be. I think there will be there is always a question of both what we do theoretically and also what's feasible and affordable to do experimentally.
Right.
And these will be serious issues.
Right. All right, great talking to you, Michael. Thank you for your insights on these issues. Michael Dine, everybody. Thank you. All right, so the final section of the program, we're going to turn to an approach to gain insight into some of these questions that's coming from a somewhat different angle, from the study of black holes, sort of an extreme form of gravity. And for that conversation, we are pleased to have Andy Strominger. He has numerous awards, including the Dirac Medal and the Breakthrough Prize in Fundamental Physics, and his work has shed light on the black hole information paradox discovered by Stephen Hawking. Please welcome Andy Strominger.
Hey, Brian.
Andy. So great to see you, Andy. And in this third part of this conversation on the search for unity, the path toward realizing Einstein's dream, and a more modern version than Einstein even thought about it, We're going to turn to the study of black holes. And before we get into the details of that subject, I mean, just quickly tell us, I think most everybody here is familiar, but, what is a black hole? And moreover, what was Einstein's view about black holes? Was he into this possibility? It comes out of his equations.
Yeah, so if you're on the surface of the Earth and you want to get into outer space, you have to jump at 11 kilometers a second. On the moon, it's a little easier. If you jump at 7 kilometers a second, you can go on forever, escape the gravitational pull of the moon. But if you have enough mass in one place to get away, you would have to be able to jump at the speed of light. And Einstein told us nobody can ever go faster than the speed of light, and so nothing can escape from a region of space-time where gravity is that strong, not even light, and therefore it's called a black hole, because it's black, light doesn't get out.
And the first solution to Einstein's equations was, in fact, a black hole. Schwarzschild found the solution. And Einstein encounters this solution to his own equations.
Yes.
And what does he say? What does he think?
It's an incredible thing. I mean, the solution was found just a few months after the field equations in complete form, exact solution of the equations. And we spent 100 years trying to understand it. And Einstein himself, the great man, 25 years later, wrote a paper in which he said black holes don't exist. And it's not because Einstein was stupid, it's because it was just they're really vexing objects. And we've been trying to understand them for 100 years. We understand a lot about them. We know they do exist. In a spectacular development last month, we saw a picture of it.
Can we bring that picture up? Yep, there it is.
Yeah. Warmed all the hearts of those of us who've been working on it for many decades. And, but there's still huge puzzles about a black hole, which came up with Stephen Hawking's work in the 70s. And those we are still very confused about. And oddly, string theory has had a lot to say about them.
And string theory in the hands of Andrew Strominger has had a lot to say about that, and we'll get to that. You don't have to, you're modest, I understand. But we want to get to the incredible insight that you and Kerman Vaffa had about black holes. To get there, can you take us back to one particular puzzle that was first articulated by John Wheeler, which had to do with these ideas of entropy in black holes?
Yeah, so a black hole is a very kind of perfect, simple object. It's really kind of a hole in space, which is very perfectly described by Einstein's solution of Einstein equation. And in that way, it's very different from, for example, a star. So if we take two stars of the same mass, they will differ in innumerable details. They will have different composition of molecules. The molecules will be moving in different ways. But black holes are just every black hole of the same mass, and they also have a spin, is, according to Einstein, according to their equations, exactly the same. And this puzzled people, and the great John Wheeler, who also invented the word black hole, described this by saying a black hole has no hair. That is, it's a featureless object. So if you have two bald people in the room, you can't distinguish them by their hairdos. If you have two people with hair, you can say one has a short haircut, the other one has a comb over, whatever. There's many different distinguishing features. But so stars are like people with hair, and black holes are like bald people. They're all the same. And, well, if you can't see very well.
So he envisioned, if you say through a cup of tea, I think is the metaphor that he used. You take a cup of tea and you sort of throw it into a black hole. He was worried that the information carried by the tea, the entropy, if you will, the disorder carried by the tea, would have no way of showing up inside a black hole, because like you say, it has no hair and they all look the same.
Right.
So this then was a puzzle that you could sort of get rid of entropy by throwing it inside a black hole, and it would be gone from the universe. And his student, Bekenstein, began to think about this, and he gave insights that ultimately led to your work. What was his view of this puzzle?
Well, they were very bothered. So going back to Newton and before, there is an idea which is very important to physicists, namely that there are laws of physics. And moreover, we like to think that the laws of physics govern everything that happens, if we knew all of them and if we had perfect knowledge. And part of that is that information should never be lost. Things can't just disappear. And so if you threw a cup of coffee or a computer or your diary or something into a black hole, according to the way that Einstein would have described them, there's no trace of it left. It's just vanished. And that is antithetical to everything that physicists would like to believe.
So what do we do with that puzzle? So do we have to bite the bullet and say that information's gone and we just have to deal with it, or what do we do?
Well, the story got substantially enriched due to the amazing work of Stephen Hawking in the 70s. The missing piece in this discussion was the inclusion of quantum mechanics. And so Stephen asked the question, well, what happens if you have a black hole in the real world? And we know that a black hole, everything is subject to the quantum mechanical uncertainty principle. It allows no exceptions. And so a black hole itself is somewhat uncertain. And the location of the horizon of the black hole, the edge of it, wobbles around a little bit, has some uncertainty to it. And that allows things to kind of slip out. Quantum things can slip out. And the way that they slip out was described in a kind of breathtakingly simple and elegant paper by Hawking in the mid-70s. And it had a very precise formula. Maybe we could see that formula. And it is one of the important formulas in, I would consider it one of the several most important formulas that came out of the 20th century physics. Stephen has it on his gravestone inscribed.
Is that true?
Yes. It's on the floor at Westminster.
With all the terms?
Yes.
Wow. I wonder what that cost. But yeah.
I think somebody else paid for it.
Probably, yeah.
It's on the floor. It's on the floor at Westminster Abbey, above his ashes.
Right. Yeah, good.
It's a very important formula.
So can we just talk a little bit about that formula? So the S in there is entropy.
We can think of this as a formula for how many gigabytes you can put inside a black hole. Mm-hmm. And it turns out, if you want to have a smartphone with more gigabytes, the size, the number of gigabytes you can put into your smartphone is proportional to the volume inside. You put the little chips in there, you fill it up, it goes like the volume. This formula isn't like that. It's a formula for the gigabytes that you can put in a black hole, and it's proportional to the area. So it's as if you're only allowed to put chips on the surface of the black hole.
Right. And that's surprising, because the formula goes against our intuition, right? That the amount of information, the amount of stuff should be proportional to how much volume is there, but it's saying it just goes like the area.
Right.
Now, when we study thermodynamics and entropy as undergraduates,
If I could interrupt for a
Yeah,
second.
please, yeah.
It's a lot of gigabytes.
yes,
All of the gigabytes in the Google data banks could fit inside a black hole a trillionth of an inch. They're thought to be the best information storage devices.
now if you did that, it might
can
be hard to
exist.
get hold of that information, but
Maybe hard to
maybe
get-
Google
maybe
has
hard
a
to
way
get
of
it out.
doing it,
Yeah,
right?
yeah.
But so it's a lot of information, but it scales in a funny way. It doesn't go with the volume; it goes like the area. But the point I was making before is that when we study thermodynamics as undergraduates, we're told that entropy, and it's related to information, is a count, if you will, of the different ways of rearranging the ingredients that make up whatever system you're studying.
Yes.
So a lot of entropy means there's a lot of rearrangements that macroscopically all pretty much look the same. If it's low entropy, then there are fewer such rearrangements.
Exactly.
Now, you mentioned before that black holes are like the simplest thing, right? There's a horizon, but there's kind of empty space inside. So the puzzle still is, what are we counting
Right.
in that formula?
Right.
And
So-
you gave deep insight into that.
Yeah, so I just want to rephrase that, according to what Einstein and Schwarzschild, the black holes and Wheeler, they were the simplest, most featureless objects.
Right.
And then according to Hawking, they were the most complex conceivable objects with the most structure that you could possibly have. So this was a huge puzzle, and it sat there for decades. Many people lost a lot of sleep over it. We didn't know what to do about it. And then string theory came along and had something to say about it, and that was a surprise. But maybe it shouldn't have been such a surprise. As you discussed earlier, string theory started out, we're scientists, we're exploring the unknown. There's no roadmap. We just explore everything, and we might find something that we didn't expect. Columbus was looking for China, and he might have been disappointed when he found America. But in retrospect, it was a good thing. And so we started out with strings, and Brian was, in the beginning, talking about this picture of quarks and leptons and neutrinos being made of strings. That picture could be right. The jury is still out. But later on, and I would say actually this began in a wonderful collaboration that Brian and exciting collaboration that Brian and Dave Morrison and I had some years ago, in which we found that strings, in between becoming quarks and leptons, could turn into little black holes. And then you put a lot of them together, and we say, hey, this is kind of interesting. They can turn into little black holes. Then we started studying how they put them together, and we could eventually learned how to make big black holes out of them. And we learned in that work, this was also the beginning with Brian and Dave Morrison, or many people. It takes a village. There were many people involved in this. But we learned how string theory can pull off this magic feat of describing an object which at once looks like an empty hole and a maximally complex object. So in some way that can be described with very precise mathematics, something is both incredibly complex and incredibly simple. When something gets very complex, it becomes simple again.
So with that, you gave the world really the first way of quantitatively analyzing the rearrangement of ingredients that, if put together in the right way, yield in the right circumstance, a black hole.
Right.
So many viewed this as a kind of key moment in string theory because while it's not predicting an observable feature of the world that we go out and sort of directly measure,
Yes.
it is making contact with a
Right.
quantitative feature of the world that was already on the books for decades. And this is the first time that there was a way of understanding it through a
Right.
fundamental theory.
Right, right. So string theory found a solution to a problem that had been posed in a completely different field. Now, this solution, this trick that string theory has for accounting for all the gigabytes in a black hole, we don't know if the trick, it's the trick that is actually used by M87, black hole M87 that we just saw a picture of, but we didn't know there were any tricks. Now we know that there's one trick, and we're trying hard to understand if M87 uses the same trick that string theory uses. So we can extract lessons from string theory about the real world, and that's something we're working on.
Yeah, so this is now, as no doubt you follow the news, this is a black hole, a real one, that's what, 55 million light years away in a different galaxy, M87, now observed making use of these radio telescopes that are scattered around the globe. Is it conceivable that we could use even more precise versions of these observations to make contact with some quality of string theory that would be kind of iconic to it, that might actually single it out as the unique or among the few possible theoretical frameworks for understanding the observations?
It's possible, and we're trying, to make a link between this picture and the ideas in string theory. And when we did this calculation in string theory, it was a very complicated calculation. A lot of mathematics, algebraic geometry, long, complicated calculations. At the end, we got perfect agreement, so we knew that we had done it right.
Perfect agreement with Hawking's formula.
Perfect agreement with Hawking's formula. So you could describe Hawking's formula as, again, going back to, you have a smartphone, you start putting gigabyte photos into it, you put 16 of them in, and then you can't put any more in, and you deduce that your smartphone can hold 16 gigabytes of data. You don't know how it stores the data. That's what Hawking did. He deduced how much their information is in a black hole. What we did using string theory, where we have a lot of control over the equations, was pry the thing open, look at the bits, count them, and show that it agreed. Now, we did it in a very complicated way. And as often happens in science, you start to realize that you can do the calculation in a shorter and shorter and shorter way. And ultimately, we realized that the key ingredient that enabled us to do this calculation was a special symmetry that these black holes have called conformal symmetry. And then we realized that some black holes in nature, ones that spin very, very fast, have this same conformal symmetry. And so probably we can understand the construction of what the chips inside it look like using the same ideas that we used in string theory. They haven't been able to deduce the spin of this yet. And we are trying to understand that. They will get a better image. We will understand the form of the image better. But we're trying to see if this black hole has that conformal symmetry the same one that we used in string theory. And so we've written there's a chance that that will work out.
Yep.
And there's a lot of black holes out there. There's thousands or millions of them up there. This is an image with only 16 pixels. I'm expecting that this is the beginning of seeing black holes.
Right.
This is like not even a black and white TV. I'm hoping that we will get high resolution images, and we will see many black holes. Some of them we know are spinning at nearly the speed of light and have the conformal symmetry. And so we've made some predictions for exactly what the black hole will look like, the detailed pattern of the polarization of the light and the shape of the image and so on.
And in principle, this could be seen, and it would be an interesting
Right.
link.
So that is our prediction of what the polarization, the light that comes from the black hole, I did with Alex Lipsowska, Delilah Gates, and Dan Kopetz, what the polarization of the light will look like. If you were looking down the barrel, actually we're looking at 15 degrees, so it's actually an even more complex pattern.
Yep.
But there's a very definite prediction. Now, this is not proof of string theory,
Sure.
but it is how science works. It works in unexpected ways. And we're talking to the Event Horizon team about how to best set up the
To actually look for
telescopes to try to look at this. And
So we're coming toward the end of the discussion. There are a couple other things I wanted to discuss with you before we conclude. So in part one, we spoke to Marcelo Gleiser about the general idea of unification, and starting with Maxwell and electromagnetism and going ultimately towards string theory. And he mentioned this possibility that, there are perhaps islands of knowledge, and maybe there are limits to what we can ever figure out. In part two, we spoke to Mike Dine about trying to make linkages between the unification program and more, bread and butter particle physics, supersymmetry, things that we might actually see at the Large Hadron Collider. And that program has yet to be successful.
Yes.
So one way of looking at these sort of first two parts of the conversation is, great try, but you're sort of not really getting there. In my conversations with you across the decades, you were one of the most optimistic.
Would you have said that to Columbus?
Yeah, what's that?
Would you have said that to Columbus when he came back?
Well,
Great try, but sorry, I wanted China.
Exactly. So that really speaks to your optimism, which has been completely clear to me over many decades. But just to give a sense, where do you stand on your view of string theory? Is it not? Has it reached what you'd hoped it would by this era? Is it in some ways yes, some ways no? And what's your prognostication going forward?
Well, so there's a view of the nature of physics that perhaps started in the beginning of the 20th century, that progress in physics was about understanding things. It's called reductionism. Understanding, molecules are made of atoms, atoms are made of electrons and protons, protons are made of quarks, and then we go down to strings. That's the reductionist program, but it's a really kind of one-dimensional view of what science is. And the original idea, which many but not all people had, of what string theory was good for, was it was the final resolution of the reductionist program. Now we knew what everything was. We found the strings. That's the end of it. Physics departments around the world can shutter their doors. That's not how it works. We keep exploring. We keep finding new things. Strings had to be explored. We're still exploring. We found other things that we didn't expect. We found out about black holes. We found out about holograms. We spawned new fields of mathematics. We, been used to describe superconductors. All kinds of wonderful things that we learned. And in fact, I think that the idea that people were excited about back in 1985 was really a small thing, to kind of complete that table that you put down in the beginning of the spectrum of particles, and then we could say, okay, this is the last year of the World Science Festival. It's all done now. We've got, string theory was really the beginning, and what has happened. So we didn't do that. We didn't predict new things that were going to be measured at the Large Hadron Collider. But what has happened is so much more exciting than our original vision.
Right.
That is, we've learned in the process of trying to understand what makes up a black hole, it turns out the interesting things were not the small things, but the big things. M87, this thing, you could drop our solar system in it and not notice it, and we don't understand it.
Right.
So we've learned a lot about the big things, and we've learned things which we sadly don't have time to go into, but about the nature of space and time, and quantum mechanics, and we're getting little hints of a radical new view of the nature of space and time, in which it really is just an approximate concept and emergent from something deeper. I mean, that is really, really more exciting. I mean, it's as exciting as quantum mechanics or general relativity, probably even more so.
Right.
And I think that before we solve the puzzles that you've heard about tonight, we will have a revolution in the way that we think about the universe, at least as profound as what was brought on by quantum mechanics and general relativity. And I would trade that for a slightly lengthened list of elementary particles any day.
Great point to end on, man. That is spectacular. Andy Strominger, thank you. Great conversation. Thank you, folks.